So we have been testing the hypothesis where we compare the means of two populations. Now, in the same vein, today we will look at comparing the population proportion of two populations, testing if they're equal or not. Similarly, assuming that the population distribution is normal, we want to compare if the two populations, their distribution have same standard deviation or same variance or not. So first, let's see how can we test the equality of proportions between two populations. So you have some yes or no question, and you have two populations, let's say population X and Y. On this yes or no question, there is a certain proportion in population X which, let's say, answers yes to it or qualifies for it, while there is a different proportion py for the second population. Now we know that if we take a sample from X or Y, then this variable is a standard normal variable, where this is the sample proportion. So you picked a sample of size nx, and obviously in the sample you can get many different proportions based on your luck. So sample proportion is a random variable, but its statistical average of the sample proportion, its expectation value, is going to match with the population proportion. And its variance will be given by this number. So this whole thing becomes a standard normal. Now, same comments apply to population Y. And if you make the difference variable, so this is the sample proportion of population X, while this is the sample proportion of population Y. If you make the difference, then this will be again a normal variable, and its expectation value will be equal to the difference of the two population proportions. While for the variance, you have to take the average of the two. The variance simply add in this case. So this is a standard normal. But we will always be testing for the question that if the proportions are equal or not. So for us, test this null hypothesis that Px is equal to Py, or I can write it Px minus Py is equal to 0. So in other case, the starting assumption would be that the Px is equal to Py, which is equal to some value P naught. In that case, this would be 0. Our expectation is that when I make the random variable from the two samples, it will be centered to get the standard normal. I don't need to subtract anything. Naturally, the difference is centered around 0. So this would be the standard normal which we will be using, because this is always going to be our null hypothesis, that the two population proportions are equal. And we are testing it against the alternate hypothesis. For example, it could be that the px minus py is greater than 0 or less than 0, whichever you want to do. Same as this. So what would happen is you have this standard normal. So if you compute this variable from your data, so what you have in your data, you have these, when I put a hat, these are sample proportions. And if this number, if the data is large enough so that this thing is expected to be bigger than 5, which will always be, we will always assume that we have such kind of data, then this can be replaced by a sample value. But we are assuming that P naught is same for population X and population Y. So which P naught, which sample value should I take? Should I take the sample value? Should I put P naught equal to the sample value coming from X or Y? Well, obviously I should, both are some samples, both are giving me some statistical information. So I should make use of maximum amount of that information. So what I do is instead I compute this P naught hat, the sample estimate. So what is this? This is the sample estimate of sample point estimate of population proportion, which is assumed to be same for px and py, but some information is coming from the sample coming from population X and some information from the sample coming from population Y. So I make a weighted mean. So I do this to compute, to take out, to access maximum information in my data, in my sample data, and take this average value and put it here to compute my standard normal. Now this is a p hat. There was no hat over here, but now this is the hat which I have just computed. And this would be the normal. Now, when I'm testing against, for example, this, I'm expecting that my standard normal, this variable computed, this computed from data, should be close to 0. So I'm expecting it to be somewhere here at z is equal to 0. But obviously, it will hop. There's a chance that I can fall here. When I'm testing against this, that px minus py is greater than 0, then I'll accept this, accept h1 if I see a number way down here. So again, some critical value. This would be your significance. Because this could happen only with a very small probability that I see a number and I start suspecting that it didn't happen just by this normal distribution allowing it. It really happened because px was really greater than py. Px minus py was expected to be somewhere here. So uh, what I need to do, I can write the whole test here. H naught, these are the uh, population proportions. You are assuming in your null hypothesis they are equal, and you are testing it against, if you're testing it against this, then simply p hex, you compute this from your data, and if this is greater than z alpha, where z alpha again is that critical value for which the probability of z lying above it is alpha, then reject. If this is true, then reject h naught with a significance alpha. Similarly, you can look at the other side. If your h1, if h naught would always be like this. But if your h1 is, this is zero, less than 0, then reject if this variable is less than this critical value, minus of that. Similarly, you can divide it as we have been doing. You can test the equality against a two-sided alternate that either px is bigger or py is bigger. Then you can divide the significance at the two ends and reject the null hypothesis if you see a number here or a number here. So we can do, for example, let's do an example. So this is problem 10.15 from Newbold. You have, well, someone did a survey in the UK and the US. So X is, let's say, is UK, and US is Y. They did a survey on 900 participants, interviewee in each country, and asked them how hopeful they are about the economy. So in the UK, they found that in this sample, 66% were hopeful, while in the US, 60% were hopeful. Now the question is, given this data, can we conclude that people in UK are currently more hopeful about economy. Because this is just a point estimate, a spot estimate. We have to put in, there's like evidence which we see here, looks like that the people in UK are more hopeful, but we have to put in some numbers to quantify this evidence which we are seeing in our sample. So we make a point estimate. Well, first of all, let me write what are our as a hypothesis. So the null hypothesis, as always in these cases, is that the two proportions in the population are equal. This I can also write px minus py is 0. While the alternate, which I want to prove, for which I want to gather evidence, is that UK proportion is bigger. Now to run this machinery, I have to compute this given the population, this px hat is the population, is the sample estimate. I have to compute this normal variable. Now here, I need this p naught hat. This is the point estimate of assumed equal population proportion. And as I explained above, this you compute by taking the average, weighted average of the both samples. You're assuming that this population proportion is equal, so you get most evidence which you have and compute this. You have to make a weighted average. In this case, since the two sample sizes are equal, so I don't need to weight. I don't need to weigh. I can just simply compute the simple average. It will be equal to the weighted average according to formula. So I get 1.26 over 2.63. And when I put this number here, since nx and ny are 0, I can call it n, which is 900. So I get over n, just adding these two terms because they are equal. And over here, I just need to plug in the numbers. Two times 0.63 coming from here. This gives me 2.63 as my observed z-value. Now I can compute that how strong is my evidence that the people in the UK are more hopeful. So just compute the p-value for this evidence. And that is simply probability of z being greater than this observed number. That is the p-value. And when I compute this probability, I get 0.004. So that's the p-value, which is fairly small. That means there's a very strong evidence. Only 0.4% chance of the conclusion that people in UK are more hopeful being wrong. This conclusion can be wrong only with a probability of 0.4%. I can do another example. Suppose you are given, again, you have to test this in the population, that the population proportions are equal against, let's say this time, that px is less than py. And from your samples, you get this, that the proportion of whatever thing you are looking at, proportion in population X in your sample is 0.39, and there were 500 subjects from the population X which were chosen in the sample. On the other hand, proportion in the sample from Y is 0.42, and you sampled 600 people from there. So you will have to compute this point estimate for the assumed equal population proportions. So 0.39 times 500 plus 0.42 times 600, nx times x, ny times px times nx, py times ny, divided by nx plus ny. So zeros just cancel, and I get which is 0.406. Now I have to compute this variable. I put in px minus py. Well, let me write it down. And what I can do, I can take this common. And I have 1 over 500 plus 1 over 600. Because that thing is common in the numerator in both. Now this number, if I compute, is so this gives me 6 plus 5 over 3000, 3666. And when I multiply it with this number, I get 0.00088843. And when I do the numbers upstairs, I have minus 0.03, and over here I have 0.0297. So I get minus 1.008. So again, I can compute the p-value. I have got this z, that there is some evidence because z is not 0. 0 would mean that this is exactly equal. There is some evidence, but how strong is it? So p-value in this case is probability of z being less than this number, which I have observed in my data. And that, if you do look up in the tables, it comes out to be 0.157. So p-value is about 0.16, not very strong evidence. That px is less than py. Now let's consider, what if we want to test equality of the variance, of the population variance of two normal populations. So all you know is that the two populations are normal. Then what you will have, if you pick a sample from X, so you have X and Y, two populations, both normal. So there will be some population variance for population X and some population variance for population Y. But when I pick a sample from here, in a sample, I will have a sample variance Sy square, Sx square. Similarly here, you will have Sy square. And based on these sample variances, I want to say something about if these two are equal or not. So to do that, what people usually do is to construct this new variable. So f variable or f distribution. So what is f distribution? If I just take this Sx square over sigma x square and divided by the other sample, then this is f distribution. This is going to be some distribution because I know that this follows a chi-square distribution, this follows a chi-square distribution. And if I take a division of those two, I'm going to get some new distribution, and I can study the properties of that. People have made tables for it and built calculators for it. So you can always multiply random variables, divide them, and you get new kinds of distributions. You can study their properties and use them intelligently. So how are we going to use this? So first of all, this distribution has two subscripts. So nu one is the numerator degrees of freedom, and nu two, the second one, is the denominator. Because I know that whenever I have this S square, it's like a chi-square thing, which has a certain degrees of freedom. Depending on what is your sample size, chi-square distribution is different. So if I'm dividing two different chi-squares, so this chi-square has a label with it, which is the sample size minus one of this. This chi-square has a label which is equal to ny minus 1. So this guy will depend on both of these labels, which are shown in its subscript. And as I have written, nu1 is the degrees of freedom associated with the top variable, the numerator, and nu2 is the one with the denominator. And just like in the chi-square case, nu1 is equal to nx minus 1, and nu2 is ny minus 1, where this is the sample size from x, and this is the sample size from y. Now, when we will be doing the tests, so in tests, we will always be testing against the equality. We will not against, we will always be testing the equality of the two variances, of the two population variances. So that means our starting assumption will always be that the sigma x square is equal to sigma y square. Or you can say sigma x square minus sigma y square is equal to 0. And I will, for example, I can test it against sigma x square is bigger than sigma y square. So since your null hypothesis is that they are equal, so this variable will simplify a little. The sigmas over here, since they are equal, they will cancel. So you can just construct this variable by dividing the variances of your samples from the two populations. Also, we can choose to put the larger variable, larger variance from sample in the numerator. Then what would happen? I am expecting this to be centered. So how does this distribution look like? It's some star. It doesn't go negative. It's some non-symmetric distribution, kind of centered around f is equal to 1. So I expecting this to give me 1 because I'm expecting that my sample should have this feature, since I'm assuming that the two populations have same variances. So that feature will be visible in the sample, and the sample variances of x and y will be almost equal. So I'm expecting it to be at 1. So if I see a number which is much bigger than 1 over here, so you see evidence of sx square being greater than sy square if F nu 2 in your sample is much bigger than 1, is, let's say, is tending to be bigger than 1. And all you want to do is, if you get a number here, you want to compute the probability, that how probable it was to get this big value for the F. And that you can compare with your significance. If the chance of that happening was very small, then you are going to reject the null hypothesis that they are equal. So that means you never have to look at this tail, because if you choose that you will, from your sample, you will always put the bigger variance upstairs, then your F computed from your sample will always be bigger than 1. So you just have to compare it with a critical value. If this is alpha, there will be a critical value here. You have to just compare it with the critical value on the right tail, because just by arranging these this way, you will never see a number smaller than 1. And then you can test. So on the other hand, suppose if you're in your sample Sy was greater, then you will compute Sy square over Sx square, and then your alternate hypothesis would be that sigma y square is bigger than sigma x square, because this is the evidence you are seeing in your data, and you just want to quantify how strong is that. So, for example, let's check this example. So you are trying to test this kind of hypothesis that if there's a monopoly or of a few company, people call it duopoly or tripoly, depending on how many companies are in the market, then you don't see much variance in the prices because there's less competition. While on the other hand, if there are a lot of companies in the market, then you will see price fluctuations because everyone will be trying to compete with each other. So for a company, the sales for 4 years were monitored, not monitored, from the records. You find out that for 4 years, when the company had a duopoly, they had very little competition, their sales variance price of the let's say the trademark product, the variance was 114 in some units, dollars or millions of dollars, whatever. And you did it for 4 years, so you have kind of a data for 4 different years. So your sample is of size 4, and in each year the sales are different, and based on that 4 data points you have computed a sample variance for their sales. You compare it Later on, for later data, when their monopoly was broken and there were lots of other companies in the market, and for 7 years, their sales had a variance of 16. So based on these numbers, you want to test that if having a monopoly has an effect on the price fluctuations or on the sales fluctuations. So your null hypothesis is that, there's no difference. And you're testing it against this hypothesis. Since you are seeing sigma x to be larger, so there is already in your data a bias, an evidence that sigma x square is bigger than sigma y square. So you take that to be the alternate and you want to reject it and gather evidence for it and see how strong is that evidence. Now, to do that, all you need to do is find out what is the value of your f variable, f distribution. First of all, I'm going to put Sx upstairs because that's bigger. This is all you're always going to do because that's how your tables are constructed. Although if you go to an online calculator, you don't really need to do it. They will have values for the others, but it's useful if you're gonna use the tables then from the book, then it will be necessary that you put the bigger values upstairs. So we just take this and I get this number. Now, this f variable has to have some degrees of freedom. And what are those? Because nx is 4, so this is 3, and nu 2, since ny is 7, so this is 6. So I'm looking at f3 6 variable, and its value I have got 0.9. Now the question is, can h0 be rejected at alpha is equal to 0.05 confidence level? So for that, I have to compute, this is the kind of distribution. This is 0.05. I have to compute this critical value of f, for which probability of this being bigger than is equal to 0.05. And if that number is smaller than this, then that would mean that I can reject if 7.1309 is bigger than this critical value. Now, how do I find this critical value? You can go to an online calculator, but let's look at the table in the book. So let me share that. So these are the distributions for f variable. And this is giving me the critical values at 5% significance. And I have the upper one is for new 1 numerator degrees and new 2 denominator degrees of freedom. So my numerator was 3 and my denominator was 6. So 3 and 6, I picked this number 4.757. So my critical value is 4.757. Since my data is giving me a bigger value than that, this implies at alpha is equal to 0.05, H naught is rejected. And the two variances are not equal. Instead, H1 is accepted and sigma x square is bigger than sigma y square. Now let's see if we can reject it at a higher significance. Can we reject H naught at, let's say, alpha is equal to 0.01? In the book, these are the only two values of alpha for which the critical values are given. So I had found from the book this critical value for these numbers, and I found that my data is giving me a larger value, so I can reject, because what I found in my data, the value for the f variable is bigger than this critical value, so I'm landing somewhere here. So I can reject at 0.05 confidence level that H naught is rejected with this significance, 0.05 significance. And that means the two variances are not equal. Instead, H1 is accepted and sigma x square, the variance of x is bigger than variance of y. Now the question is, can we reject H naught at 0.01 significance level? The book, it cannot have all the tables. So for the f variable, it has only tables for significance 0.05 and significance 0.01. So let's see what number the table gives for this significance, and can we reject it with a bigger significance of 0.01. So this table is for alpha is equal to 0.05, while this is for 1% significance. So I have upper new one is 3 and new 2 is 6, so I have 9.78. F so that means my number, which is just this computation from data, sx square over sy square, since it's less than this critical value, because this was something like 7.13. So I can not reject at alpha is equal to 0.01. I can try to compute the p-value for this, if I go to stat track, or if I go to SPSS, they both have these distributions. Now, let me go to that screen for the F. What screen do you see right now, Osama? Yeah, that's what I wanted. And did you see in between the screen with my writing? I guess you did. But in any case, so
Mostly, what is your only the Chrome screen is showing when you're trying to change the screens. It's not showing that you're changing it.
right now you see the stat track. Tell
Yes,
me,
sir.
tell me what do you see now?
Search till Stack Track.
What do you see now?
Search the Stack Track website.
You don't see my notebook?
Now I see.
Okay. Yeah, it takes a while. Okay, let me go back to the stat track to compute the p-value. Now, uh, nu1 is 3, nu2 is 6, and f value is the one which I see in my data. That's just the sx square over sy square. And that was 7.1309. And I can see what is the cumulative probability. So it's 0.98. Let me change the screen. So the probability of this variable being, since the stat track computes the cumulative probability, that gives me being less than this variable. That's what it computes. Cumulative probabilities are always you start from this tail and go to a specific number. So this it gave me as 0.98, but what I need this. So that means this is 0.02. So the p-value, since that's just the probability that f36 is bigger than this number, what you see in your data, that is 0.02. So the p-value for this result is 0.02. And this confirms that it's between 0.05 and 0.01. Less than 0.05, but greater than 0.01. We can do another example. For that, we will definitely need the stat track. Well, you can do it using the tables as well, but you have to do a little bit of estimation because table does not have all the values in it. So let's take this example. Wait. Uh, suppose you have Sx is equal to xx square is equal to 2107, and I've changed the example, and this is equal to 1681. This is problem 10.26. And in both samples, your sample size is 10 and 10. That means you are going to construct F99, and its value is simply sx square, sy square. You put the bigger number upstairs, and it's 1.25. Now we can look up through the table. Can we reject H0, which is, and accept H1, which is, as per our evidence here, I must take this alternate at alpha is equal to 0.05. So if I go to my book, and I see at 5% significance level, I have to look at 9 and 9. So the value is 3.179. So it had to be bigger than 3.179. But my number is 1.25. So I cannot reject it at 5% significance level. If it's not, it can be rejected at 5%, then it definitely cannot be rejected at 1%. So since F99 0.05 is equal to 3.179, so since this critical value is 3.109, while what we got is less than this, so we cannot reject. It's not. So let me stop here, and next time we will start with a completely new topic.
Okay, sir. Thank you.
Okay.